Okay, so what we're going to talk today. Let me start from the thing that I forgot to tell you last time. I really forgot, so that is, I even gave the problem on that. I forgot to tell you this algorithm. The algorithm is called DigitSort. No. I don't know. Okay. So what is their idea of the DigitSort? Is that suppose that your elements are all less than some value n. So you have an array and all elements are less than equal to n. How to sort them? So for example, there is a problem in the homework where you have digits and you have to sort digits. So here is the way how to sort it. You create an array from 1 to n, and then you just go by each element and increase CAI plus plus. So you just count the number of AIs that are there. So for each value, you count how many times it is in array A. So to sort, finally to sort the array, you just go through all this array C from left to right and output AI as such number of times as it is written here in there. So for example, if you have X, so we write X C of X time. C of X time. Okay, so there is this is a DigitSort. Other questions here?
Yes, it is. So we count the number of a number is mentioned in the array, and
so you need to sort array A.
Yeah.
Okay, but you know that all their elements are less than or equal to n.
Okay.
Okay, so for that you could create a special array which counts how many times this integer is in array A.
Yeah.
Okay, and afterwards you just pass through this array now and output how many times each integer was in array A.
And how does it sort the array?
Okay, let's take an example. So for example, I have 3, 1, 3, 2, okay, array.
Yeah.
So I have 3, I know that m is 3. So what I'm doing, I go 3, okay, so I should increase the third cell here. Okay, then I see 1, I increment the cell here. Then I see 3, I increment the cell here. And then I see 2, I increment this 1. So how to get the sorted array back? You just go from left to right and see, okay, there is one number 1. Let's put it. Okay, how many numbers do we have? Okay, we have one number 2. And finally we have 2 numbers 3. That is your sorted array right now.
Okay, I think I will just read it on my spare time because I really don't want to stop the lecture because I don't get it.
We are not rushing today, so what I explained and what I explained, the better is for you in the sense that in both senses the first you will understand everything, and the second that you will have less problems in the homework. So it's double your profit. So what is the question, really?
Can you provide us another example, please?
Okay, sure. How much array do you want to have? How big array?
5 elements.
5 elements. Okay.
Maybe.
Can you tell me which?
It's not matter, but 2,
Okay.
4, 1, 3, and 0.
Okay, good. So
as far as I understand, we just put the frequency or a particular number into the
in array C, yes.
In array. Okay.
So like let's try here. So we know like 0, 1, 2, 3, 4, 5. Let us think that we have 5 elements here, and let me like change 4 to 5 so it will be probably more cleaner. So I calculate how many each element is in this array. So I have 2, 1, 5, 1, 1, 1 is 1, 3, 1, 0, 1, and 4 is 0. Then, to give you back the sorted array, I just came by with frequencies from the left to the right and output there how many times this element exists in the array. So here it will be 0, then 1 time, 2 1 time, 3 1 time, 4 0 times. So there is nothing here, and then 5 1 time. So if, for example, we had, like, I don't know, here 5, then our frequency array will be like that. So we will have 0 0 times, 1 1, 2 1 time, 3 1 time, 4 0 times, and 5 2 times.
Could you please tell us what is the complexity of that kind of algorithm?
Okay, so you can tell me what is the complexity of this algorithm. Suppose that the size of A is n, and here is m big.
Well, the time will be linear, but also it will take the memory of m. Excuse
The time will be not like, it is not linear, right?
I also have an idea, because if we use arrays, not list, the array has this property that we use a constant time to reach every element, so it's going to be constant.
Okay, I mean, yes, it's constant. So there are two additives. The first one is that, so how the algorithm works. It first pass through whole array to count the frequencies. So this is n. Okay? And then you pass through array C. So what is the complexity of the second step?
Well, it is n plus m, but still it is linear, or...
Yeah, it is n plus m. This is very important, unfortunately. So, for example, if n is 10 to the power of 5 and n is 100, then your complexity will be overwhelmed by this m. So you can't throw m away. You can't say that this algorithm works in all of n time. You just have to tell that it works in all of n plus m. So this is the question about complexity really here. So you should, in your complexity, you should count all the variables that are there. So you can't tell that this algorithm works in all of n time. This is not how it works. You just say that this is all of n plus m.
Is this algorithm works only for positive numbers?
It depends on the range of the value. So for example, right, if I make here bigger than -m, right, I know that AI lies between -m and m. I will just create an array of size from 0 to m. And then to count the frequencies, I will count there only for positive numbers, kind of. I just increment AI by m and ask to ++8. So I transform array into array with integers bigger than 0 and output them.
So in general case, when we do not know what is -m and m, we need to find this first, and the complexity is more complex as a result, yes?
Kind of, yeah. This depends on whether, so for example, if you know that your integers are not very big, like you have an idea, I don't know, like you have the special biological data that, for example, I don't know, the number of, okay, that's not where the thing, but like, for example, let us take from biology, the number of nuclear acids, they're 21, as far as I remember. I'm not 100% sure. So for example, you have to sort the nuclear acids that are given you as an input. You know that the number of nuclear acids is finite, and you know that this is small. Then instead of running the standard sorting algorithm, you just can map nuclear acids to integers, and then just say like this nuclear acid is 0, this nuclear acid is 1, this nuclear acid is 2, blah 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 blah. And then you just go through all the array with nuclear acids and maintain this array C of frequencies. Like, otherwise, if you don't know any constraints on your data, there is no way you can do this. Because if m is big, your complexity will be dominated by m. So you have to run like standard sorting algorithm, which is an logarithmic function.
Okay.
Now it's clear. Yeah.
Okay, good. So yeah, so you should use this algorithm only in the case that you know that your elements are not big enough. Or yeah, if you are given some problem, I don't know, like from biology or I don't know from where else, and you have a suspicion that the elements are not very distinct. You just can go through all the array and maintain like minimum or maximum. Also, you can use let me go forward a little bit, and for example, instead of C array, you could use hash map. Hash map, it transforms keys to values. So you just simply has to, for hash map, you just simply has to say something like that in C++. It's not Java, but like hash map AI equals to 0, and then when you need hash map AI ++. So in Python you will have similar things. I think it's named hash map in Python. In Java it will be a little bit more complicated because hash map doesn't work like that exactly. so what is the idea of the hash map? Is that it can point from, it can store keys to values, where keys can be of size, like of very big size. However, that you know that the total number of different distinct elements is small. So this thing works like to get the value from hash map AI costs you O of 1. It will be not as fast as your array of frequencies, because array of frequencies, you just have a standard array and you don't have to do anything. In hash map, it's a little bit complicated. So it costs more than frequency, but it still can cost less than calculating their standard sorting algorithm and logarithm. Because here you have O of 1, then you will have O of n plus m, where m is the total number of different values. So like here will be sorry. I'm wrong, not values, like keys. You transform keys to values, so you index here by the key. So AI is the key here. Okay, did you understand anything, or it confused even more? So there are no questions right now.
No, I'm sorry, I was dying from coughing. Yeah, it's fine. It's clear.
Good. So let us I will give you a brief thing about DigitSort so that you know that it exists. I'm not asking you to write it anywhere, but like in general, you should understand that this thing exists. So like when you need it, you will read it more properly in the corresponding. So suppose right now that you have values AI less than m big into the power of k. So it can be for example, right? So for example, why it is DigitSort, right? For example, it can be integers, and you have like for integers, it will be 10 in the power of k. So some value. So you know that the values are less than 10 in the power of k. Why I chose m here is that because each AI can be split into the boxes, k boxes of each of them less than equal to m. I think even less here. Okay, for 10, this is exactly how the integer is represented in digits of decimal. Okay, how to do that? So how to sort this, like, what is the first idea that comes to mind afterwards? Let us sort the elements by the first value. So you calculate the frequencies. So this is AI1, AI2, AI So you sort by, you calculate the frequencies for AI1. So this is C, 1, 0 to M minus 1. And you calculate the frequencies. Then you go through, like, you calculate the prefix sums on this. On this array. On array C, you calculate the prefix sums. Then you just go through array AI and check their AI1. So we say that array result. So you calculate C at first, it's CAI1 plus plus. Then you calculate the prefix sum of this, so S I is equal to C0 plus Ci minus 1. And then to put it back, you just tell, okay, here is array R in which we compose the resultant, and we say RSI plus plus and set the value of AI. Oh, sorry. No, not SI, but SII1. So what is happening here? So we calculate the frequencies. What is this prefix sum array? This prefix sum array shows us where should be the first element with the corresponding value, on which shift in the resulting array should be this value. Obviously, value I should be in the resulting array at the position C0, C blah 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 blah, Ci minus 1, like exactly this. So this is the first position of I. I minus 1 is corresponding, all I minus 1 should be before, all I minus 2 should be before, etc. And all zeros should be before our I. So that's why we can calculate the prefix sums. And then we know at which position should be each element. We just pass. Is element I, AI, we take the position, like the shift in the array R, where it should be, and increase it by 1, and set it to, so yeah, so should be like that to be more precise. Like that. You set AI here, and like you increment by 1 the position. Like let's understand this, and like you can ask me questions. So like let me try to give you an example. Probably it will be much easier. So for example, you have 3, 3, 2, 1, 1. I consider that k is equals to 1 right now. So like k is equal to 1. So we again calculate C. We calculate 2 1s, 1, 2, and 2 3s. And then I calculate the prefix sums. So the first position where 1s should start is 0. The first position where 2 should start is the number of 1s, which is 2. The third, like the 3s are going to start from the position of where 1 and 2 are. So this is 3. So now let us go. So this is array C, this is array S, and we have an array R. So we take 3. We say, oh, it should go to position 3. The first 3 should be in position 3. Okay, I put here 3. Increment this suffix position. So the next 3 will be later at position 4. Then I go to 3. I take 4. Okay, it should be in position 4. I put 3 here. And say here 5. Then I take 2. I know that the position of 2 should be at 2. So I just set it to 2 and increase here. Then we come to 1. The first position of 1s is 0. So I'll put it here. And increment it by 1. Then I come to 1 again. And I see the next position of 1 should be at position 1. So I write here 1. So that's how I kind of did the digit sort, but a little bit in another manner.
I have a question of how it works with the m in the power of I guess 2 or 3. So like we have, I don't know, numbers like 21, 47, etc., etc.
Okay, yeah.
Okay.
Yeah, so here is, for example, it will be not like this. It will be 31, 34, 20, 22, 14, 12.
And is it going like in cycle till it is sorted, or how it works? Yeah.
I think I don't understand the question, but like right now I'm giving you the idea of what to do.
Yeah.
So so why I did this way? Because right now their elements are a little bit complicated. They consist of 2 digits. So you can't do the way as we did previously, just look at their count array and like restore array itself. So like by that, we will take 3, it will pass here 31, here 40, 33, here 22, here 14, here 12. Okay. Like you would try to think, okay, so how to do this work? Let us first sort by the first digit, then by the second digit, then by the third digit, etc. Unfortunately, this doesn't work as it is because you have buckets here. You here have buckets, and for each bucket here, so this worked in n plus m. But on the next step, it will work n1 plus m, n2 plus m, n3 plus m. So if you do it in straightforward manner by the first digit, then by the second digit, then on each step, you will have much more m's than you want to. Instead of that, I propose it to do vice versa. So we start from the smallest digits, sort array by the smallest digits, and then sort array by the second to the n digit, then the third to the end, and etc. until we come to the first. Why does it work? We didn't talk last time about stable sort. So what is stable sort? Stable sort is an array. Oh, sorry. Stable sort is the sort that maintains the same position of the same values. So, for example, this algorithm is stable because, as you can see, for ones, these elements were equal in the sense to 1. And 1, 4 comes before 1, 2, as in the first array. Stable means that, so that the equal elements do not transpose to each other. They come to the result as they are at the start, at the same relative position as they start. Okay, so merge sort was stable. For example, from the last lecture, merge sort was stable, but Greek sort was unstable. And here we can take the idea that our algorithm, like that DigitSort algorithm, is stable. So let us consider an example. Okay, at first I sort by the second digit instead of the first one. So I start not from the left, but from the right. So how many ones here? Okay, we have one at the end. How many twos? There are 2 twos here. How many threes? No threes. And 2 fours as the last digits. Then I calculate there's prefix sum, so 0, 1, 3, 3. And then I put R. So I take 31, so the first position is 0, so I put here 31. Then I take 34, its first position is 3, then I put it here, 34, then 22. The first position of 22 is 1. Then 14, like we already have 4 here, so it should be 4 here. And then we put position here. And then finally we have 12, we put 12 here. So we sort our array by the second digit.
And do I get it right that the second case in the sum array should be 2 as well? It's like 0, 2, 3, 4 in the sum array.
Why 2? Why 2?
Because we have 2 twos.
No, this prefix sum until I minus 1. So the first is just 0.
Yeah.
The second one is the sum of the first array, so it's 1.
Yeah, but then we have 21 in the array R, 22, sorry, and then we have 12.
Yeah.
So it is increasing by 1, so it shall be 2. Or
No, this is exactly what I wanted. I wanted to sort by the second digit. So as you can see, 1, 2, 2, 4, 4.
Yeah. Okay. So in the sum array, you increased the last one to 4, like the last one is 4.
I mean here. Yeah.
Yeah.
Okay, here I should have increased by 2.
Okay. Then I get it right. Thank you.
Yeah. Sure. I just saw that it's clear, so I didn't do that. Yeah, it should be 2. Yeah. Exactly. So by that, I kind of force that the elements that are going to be compared with the first digits, they will come to the order by the second digit, because I already sorted by the second digit. So these elements are sorted by the second digit. So if you take, for example, 12 and 14, 12 will be on the left to the 14. So when I sort the next time, 12 will be before than 14 because this our algorithm is stable. Okay? So like when I do here, I calculate C as 1, 1, two ones, 1, 2, and 2 3s. This is by the first digit. Then I take as 0, 2, 3, 5. And then I want to get array R. So we have coming through the 31. This should be in position 3. Here goes 4. 22. We take 22. We see that the position is 2. So we put here 2 and increase by 1. 12. The first, like, it should be at 0. So we increase this by 1 here. Then 34. We see that there are four of the, it should be at the 4th position. So I write this in 4th position and increase by 5. Then 14, I increase it by 1 here and put 14 here. So this is exactly what we wanted. So this is exactly the right sort.
Yeah, it's clear.
We sorted array properly. So if you want to sort elements that are m to the power of k, then you do k times the algorithm from the back to the top, from the smallest digits to the largest digits. What is the complexity will be?
Just a second. 30 seconds.
Okay, sure.
Wouldn't it be the sum of n and a again?
What, n plus m?
Yeah, wouldn't it be that?
Why do you
I'm not
think?
sure.
Why it is n plus m?
Well, at first step at least before the second one.
Okay, first step is n plus m. Okay, how many different variables you see here?
I think complexity will be k multiplied by m.
And that's all?
And we need to plus m something.
So k times m plus what?
Plus n.
Plus n.
And k multiplied by sum of m plus.
Like this.
Yeah, I think so.
Yeah, that is right complexity. Why so? Because you k times do digit sort.
Yeah.
Digit sort works in m plus n, and you do this k times. So this is k times m plus n.
So is it for the whole algorithm or for the whole algorithm? Yeah, it was my question.
For the whole algorithm, yeah.
Yeah. Okay.
K times do radix sort.
Okay.
So this is, I try to explain this so that you understand that there is some other sorting algorithms that like why this happened in general. So let me give you a brief intuition, a brief idea why it was possible. So the problem is that if you have your only less and bigger than operations, as we have in the previous sort algorithm, it can be proven that the algorithm cannot be faster than n log n. Why so? Because, like, let me give you a little bit of information theory here. So when we are comparing two elements, it gives us one bit of information. AI is less than AJ, or AI is bigger than AJ. So this is one bit. One comparison is one bit. In total, there are n factorial permutations. So to store n factorial permutations, we need logarithm n factorial. Logarithm n factorial bits. So, like, you need log n factorial bits to set all the arrays, but at the same time, you have only one bit per condition. So you have to do logarithm n factorial comparisons. But logarithm n factorial is itself is n logarithm n. So using only comparisons cannot give you the algorithm which works faster than n logarithm n. However, in this algorithm, we could do faster, right? We could do in of n plus m. Why these approaches do not do not opposite each other? The thing here is that we are doing not only comparisons here. We can take a position in the array by this value. So that is why you can tweak the lower bound of n logarithm n. So it's theta n logarithm n. Is it clear? A little bit.
Kind of, yeah.
Like, the only thing that you need to get out of this is that using only comparisons, you can do only n logarithm n time. You cannot do faster. And you can prove it using some information theory. So, and this one works in n plus m. Okay. Are there any questions about sorting?
Not so far, I guess.
Okay, good. So now we come to, so we talked up to this time about algorithms, but we didn't talk about data structures. So what is the data structure? The data structure is a black box that can be operated by several operations, several requests. So we start from stack, which is the simplest data structure. I think a lot of you are familiar with stack. So like we are kind of doing right now the revision of what is stack and which problems we can solve using this algorithm.
The structure like queues, but except of the way how digits can be removed or added into this stack. As far as I remember, queues use FIFO, I mean first in, first out, and stack uses last in, last out order.
Yeah, that's true. Yeah. So what are the, like, I mean, so I hope that everybody is familiar with that because I will not spend a lot of time on that. So you have two operations. No, yeah, really, I think we will do the following. So I will split this lecture kind of into two parts, and probably we will next week we will finish earlier. So I will be talking more about like theoretical things rather than practical things next time. So you will not have a lots of homework there. So yeah, that's a little bit not in the stack thing, but like in general. So stack operates with two operations, push and pop. Yeah, and as Ekaterina told, right, it is leave for. So what it is, what does it mean? So last in, first out. So push operation puts an element to this data structure, our black box data structure, and pop withdraws the last inserted element. So stack can be seen as an infinite array which can be pushed, like push x. So we put x to the end of this array. And pop, we simply return this element. So for that, to emulate this, we have the special position head of the stack. So like probably it's much easier to understand it from top to bottom. So like that. So push of the element puts an element there, and pop element like push puts on the top of the stack. Oh, sorry, it's not head. Yeah, that's for queues. It's top. So you push on the top and you pop from the top. You take the first element that is taken from the top. Okay, how to implement this? So you create a very long array. So push x is doing stack top plus plus equals to x, and pop returns stack minus minus top. So this is the whole implementation. Yeah, you can do this thing in Python. Like I give you a hard version, like kind of hard version, which is written for Java. So the idea is the following. You take this, so this is like, I will explain you what it is equal to. So this is push x, stack top equals to x, top plus plus. A pop will be top minus minus, return stack top. So why they're equal? So you put the elements on the top and then you increase top. So in my algorithm, top will always point to the next empty cell. Then for pop, you just decrease their size and return their element that is on the top. Okay? So
Yeah.
how to read this line? You just see here, top plus plus. Top plus plus, it is that it will be incremented after. So it first takes the value and then increment the value. So it is equal to, we first take the value top and then increase it. Here it's vice versa, it's minus minus top. So this means that at first it is decreased by 1 and then is put there. So that's why you have top minus minus return stack top. Questions to stack?
No.
Okay, good. So let us solve several problems using stack. Like this data structure is pretty simple, so you can implement on your own, or you can use like in the homework, you either can implement it or use already pre-written. For example, in Java, there is a stack, for example, integer s equals new stack. They just that, you just create. In Java, there is a class stack. In C++, there is a vector that is good enough. So you have push back, pop back. In stack, I think you have push and pop. So it's already written there. Or you can do this on your own. I don't mind. Everything's fine. So consider the problem. You're given a string of brackets of two types. So you have square brackets and you have round brackets. What does it mean, the correct bracket sequence? Correct bracket sequence is that if you, so you can use it in arithmetic expression. For example, this is correct, this is correct, but for example, this is not correct. So is that for each open bracket, you have closed bracket, and everything that is inside is also the correct bracket sequence. So for example, this is open, this is closed, and this is the correct bracket sequence. Okay? Here, for example, it is open and closed, and there is empty bracket sequence, which is by default correct. Here is, you have open and closed, and between them only open bracket, which is not correct. So how to solve this problem? It appears to be pretty easy solved by stack. Is that you just go with this from left to right and just put into the stack the brackets. So for example, I want to check whether this bracket sequence is correct. So I pushed on the top their open bracket square. I pushed on the top open square, open round bracket. Then I see, oh, I have a closed bracket. Then the topmost bracket should be the open one of the same type. So I just pop it. So if I see the open bracket, I just check, oh, it's closed bracket, then I just check that the corresponding open bracket is there. Then I take the closed square bracket, okay, on the top there is a square bracket, then I just pop it. What's happening with this? So I put open bracket, square, I put open round bracket, and then I see, oh, I have a closed square bracket. But the bracket on the top is round. This means that I can't take it. I can't pair these two brackets. This means that this sequence is incorrect. So the algorithm is pretty simple. You just push open brackets. If you have the closed bracket, you just compare the bracket on the top and pop it if it is possible. If you cannot pop it, then your sequence is incorrect. Okay?
Yeah.
Okay, good. You will be having another problem on there, which is not really about the steps. So let's consider their bracket sequence with one type of brackets, so only round brackets. So we take an open bracket, put it into the stack, then we take open bracket, put it in the stack, then we take closed bracket, we pop from the stack, and etc. Note that we can do like this. It will be equivalent. So this will be +1 + 1 -1 + 1 -1 -1. So each open bracket, so we have a balance. The open bracket will increase the balance by 1, and the closed bracket will be decreasing by 1. This is exactly as how many elements in the stack right now. So we put the first in the stack, there is 1 element in the stack, and the balance is 1. Then we put the second bracket, the number of elements in the stack is 2, and the balance is 2, because it's +1 + 1. Then you take the closed bracket, you remove the bracket from the top, and the number of remaining elements will be 1. So and balance is also 1. So can you tell me when when the bracket sequence is correct. How should what are the conditions for this balance should be?
Balance should be 0.
At the end, yes, that's.
Yeah, at the end.
Yeah, at the end it should be 0.
But we also need to start from open brackets. Or, for example, if we start from closing bracket and then open bracket, this will be incorrect by balance will be 0.
Yeah, but what happened with the balance? So, okay, let's consider that. It's -1 + 1. What is the problem with the balance? You just take the balance and it is -1 here. So what is the problem with the balance? If you come to an empty stack with a closed bracket, it doesn't have the matching bracket. So like the string is incorrect. So what we should set, like for what condition we should check balance?
It shouldn't be below 0.
Yes, exactly. So balance always bigger than equal to 0. Yeah, so there are two conditions. The balance should be 0 at the end, so there are no open brackets at the end. And at the same time, the balance should be bigger than 0 at each moment in time. Otherwise, the sequence is incorrect. So you will have the problem that is based on the balance. So please be aware of that. So you will have to think a little bit. Okay. Then, suppose we add another operation. Minimum. Please return the minimum in the stack. How would you solve this problem? So there are 3 queries: push on the top, pop from the top, and tell me the minimum in the stack.
Maybe I will get the first and the last element. Okay, just give me 30 seconds.
Yeah, sure. Like, we are not rushing. You can store, I will say, you can store additional information per each element. So you can store something here. Like, I don't know how it's more preferable. I think, yeah, I think this one can be more preferable. So this is the element V1, V2, Vk. Oh, sorry, let it be. V top -1, 0, something like that. So these are the values, and we can store something in addition to it.
So at the first step, we pop element from our stack and push it to another stack. Then we pop from the first stack element and pop element from the second stack and compare if first element is
Okay, yeah, I got it, what you're trying to do. What is the complexity of your algorithm? Yeah, I didn't specify properly. I want of 1 per minimum. I want to calculate minimum in constant time.
So the variant where we have 2 last elements, find the minimum, and throw the maximum in another stack, and then we compare what we've got from the comparison to another thing that we got from the first original stack. Is not right?
Then you will have problems with the pop, right? You don't know from which stack you should take the element.
We always take the element from the first stack, and as soon as we always have the minimum of 2 elements in comparison, we will find the minimum element at the end. So just like, okay, we have, I don't know, 1, 2, and 3 in the stack. So I get 2 and 3, compare them, throw 3 away.
So, let me start. Like, we have 1, 2, 3 in the stack.
Yeah, okay, for example, 1, 2, 3. Then we have 2 and 3 and compare them.
Okay, good.
And put 3 away, and we have 2. And then we compare 2 to 1, and then we throw 2 away, so we have 1. And this is the minimum element of the stack.
Okay.
So, yeah. And this is the...
Then you are asked to do pop.
So on the last step, you mean?
No, you are asked to please pop me an element. Your top element is 3. Like, because your kind of real data structure is like that. So
Yeah.
your pop should return 3. But how did you get 3 from this?
No, I don't understand your question.
Okay, so you pushed 1 to 3, right?
Mm-hmm.
And asked for the minimum.
Mm-hmm.
What you are doing, like, this is the ideal stack. Ideal. With an oracle. It just returns, minimum returns 1.
Yeah.
Okay, what you are doing, how do you implement it? You just take 3, 2 outwards 3, then you take 2 outwards 2, then you take 1. Oh, 1 is the minimum, okay, fine, great. But then, this is your, like, this is how your stack looks right now in your algorithm. So when I ask pop, here it is return 3. How are you going to find 3 in this stacks?
Why are we searching for 3? I don't. Okay.
No, you have to do pop right now. So you did minimum put elements 2, 3 on the right stack.
Yeah.
Then you are given operation pop. This pop should return 3.
Why I don't get why should it return 3?
Because in the ideal stack, the 3 is on the top.
Yeah.
Yeah. So the next pop should return 3 by the sequential specialization of the algorithm. Pop should return 3. Sequential specification, sorry. I mean, this is the specification.
Yeah.
This is your implementation. So in the specification, you should do push 1, push 2, push 3, min, that return 1, and pop that return 3. This is what they're this is the order of their operations and what they should return. Then your algorithm is doing like, it puts 1, 2, 3, then you ask for the minimum and you put all the elements into the second step.
Mm-hmm.
Then by the specification, the pop should return 3. So the question is, how could you return 3 from this state of your data structure?
I'm sorry, I really don't get the question. Ideal specification is like the constraint. Oh God, is it something I should follow?
Yes, of course.
So I push 1, push 2, push 3 for our original stack, right?
Yes.
Then I have a question to find the minimum.
Yes.
So I do my own algorithm. I really don't get why do we have the pop3 thing?
Well,
So we should get back to the original stack.
so you want to put all these elements back?
No, but why do we have the pop3 line? I really don't get that. Shall we just find the minimum, or shall we just like pop the minimum from?
No, this is the this is the black box.
Yeah.
It should maintain the following operations. Please push element on the top, then pop, take the last element that was inserted.
Yeah.
And return minimum, give me the minimum on the whole stack. Which doesn't change the stack. It only gives you the minimum, the value. The minimum out of all values there.
So at the end, we should have the minimum and the original stack.
You need, it is the black box. So please consider it as a black box. So how your black box should respond to this line of operations? You should push 1, nothing to do. We don't know what is this. We push 2, we push 3. Then we ask for minimum. We know that in our stack there is 1, 2, 3. So by our specification, it should return 1. Okay? And then the operation pop, how it works? It takes the last pushed element.
Yes.
The last pushed element is 3. So the pop operation should return 3 by specification. This is the specification of the black box. So your black box that you are going to implement has to respond to these operations exactly as it's specified. So for example, in yours, it will be push 1, push 2, push 3. Then you operate some minimum operation. I don't know how you implement it. This doesn't care. I don't care about that, how you implement it. But pop, the next operation that will be called pop on your black box should return 3. Because the specification says so.
What if we put them not in a stack, but in a queue?
Sorry?
What if we, okay, it's just, I'm not sure that I get you right, but what if then we put the sorted, not the sorted, the elements like 2 and 3, not in a stack, but in a queue? So the first element that came there would be the first one to be popped. Or I really don't understand.
Why you are talking about queues?
Yeah, but if we do this implementation that I just told you about, and at the end, if we need the pop element to be, for example, 3,
yes,
still we need to find the minimum element, and as soon as these 3 would.
Here's minimum. You want here minimum? It should be 1.
Okay, I don't understand the question then. Okay, or we just don't understand each other.
Okay, sorry. Let me. So since we are out of time, I will explain how to do this. You just simply, with each element, you maintain the minimum on the bottom of the stack. So for example, this element will be minimum of V0. This element will be min V1 and M0, which will be M1. So at the top here we will be minimum Vt with mt minus 1, which is equal to mt. And at the same time, it is the minimum of all elements that lies below it. Then how to operate push? In the push, you add the element here, Vt plus 1. You calculate minimum of Vt plus 1 and mt and put it here. Then how to answer minimum operation? Minimum operation, we just take the minimum value that we store here. And pop operation just takes away these two values. Since with each value we maintain the minimum of the elements that are below him, nothing will be changed really much. So this is how we do this in off constant time for each operation. Clear?
So we need two stacks, and when we push element to one stack, we also need to push minimum value to the second stack.
Yeah,
also.
kind of. Yeah, you can do that.
Oh, I think we need to find minimum element in a stack what has already exist.
Yeah, I thought that too. That we already have a stack and we don't have we don't need to make the push operation, and we have like the stack and we need to find the minimum.
No, you just have lots of operations here that like this is exactly the data structure. Data structure doesn't stop anywhere. It should perform operations after operation after operation after operation. So this number of operations can be infinite, and they can be in any order.
Okay, now I got it. I'm just thinking about another problem.
Oh, sorry, that's my mistake. Like right now, I hope you understand. This is the data structure problem. So this black box should answer these queries, and the queries can be random at any moment, in some sense. So they're not finishing; that they're continuing coming. Okay.
Yeah, okay.
Good. Okay, we did not so much today, but I think it's much better for you. So I hope that you understand something and you will be able to solve the problems. So and we will continue with this next week. So I will not be doing. So I kind of split this lecture that I wanted to tell you in halves. So like the other half will be next week, but probably the lecture will be shorter. I don't know how much time we will spend on everything. So okay, I will send you the video after, and that's all.